Live. I'm Lance Farrell, the managing editor for Science Node magazine. With me is Damian Borth and Simon Keuper, Janis Keuper.
Hello.
And we are sitting, we are in Frankfurt, Germany right now. Today is June 21st, first day of summer. And it's beautiful weather, beautiful time here in Frankfurt. How are you guys enjoying the conference?
Awesome. Really great conference. A lot of people, interesting talks, and a lot of content to be covered in multiple tracks.
Yes. And having the deep learning day today brings together the crowds from machine learning and HPC, and we have had really good discussions, good talks, and people are really into it, asking in-depth questions, and we actually have taken our due and overtime in the first two sessions, but it actually was worthwhile.
A whole day dedicated to deep learning. That's true. That's new for the ISC.
Yes, very good. I appreciate you taking the time out. I know you had to go overtime. But yes, as I mentioned, today is the Deep Learning Day, so we're going to speak with Damian and Janis about deep learning. But I thought maybe we would start, if you could just kind of tell us what it's like to be a deep learning expert. What's a day in the life of Damian Borth, Janis? What's it like?
Well, starting early, as usually, and starting the day with what happens in the last weeks and days. The interesting part in the area of deep learning is in particular that the cycle of publications in this area is increasing. So people are not waiting year to year for the conferences, but rather move forward with uploading papers to archive, which then are actually on the fly available. So therefore, reading and catching up is a large portion of the day, and then speaking to your fellow colleagues and students to explore the space and the ideas that are developed almost continuously.
Okay, very good.
And that I think he already made the major point is that this field is moving at an enormous speed, and the usual cycle of journal publications that takes an entire year has been dropped over time. So now we are at archive, which is basically a live feed of what people are researching. And my day starts with looking what's new on archive. And actually I wrote myself a small AI program using deep learning to find the latest deep learning papers on archive, so I don't have to scroll on my own. So what I will get in the morning is a summary of the publications uploaded last night. So I have an AI helping me getting through all the AI stuff. And actually this is a tough business, because I end up with like 5 to 10 papers every morning. I decide I should read. Of course, it doesn't happen, so I sometimes redirect them to my PhD students and have read this and tell me what it's about. And then we have the discussion. And I think the spirit of this field is that it's extremely open. Everyone is doing open source, everyone is sharing their results, and this is a really productive environment. So you really spend a lot of time not being in the lab hacking code, but actually talking to people and look at what other people did and catching up. And usually this starts the day, and then you get new ideas and you have to reschedule. And in the end of the day, sometimes you had this great idea 3 weeks ago, and you figure out that someone else had it too, and then you start over again with the next idea. So it's very vibrant, very, very high speed.
Unfortunately, we don't have enough hours for the day to catch up with all the research. But that's an exciting time. That's something that will happen once, and maybe a second time in a lifetime. And it's exactly happening now. So why not?
Why not? Yeah, it is an exciting time. But when we speak of deep learning, maybe you can help us understand what we mean. That's not what we're talking about. Going in a submarine into under the water. Well, I've heard of schools of fish, but this is not what you're talking about. But more seriously, we're familiar with pattern recognition and machine learning, but deep learning is a special subset or a type of machine learning. Maybe you could help me understand by way of contrast or comparison. What do we mean by deep learning?
So we opened up at the German Research Center for Artificial Intelligence a deep learning competence center in 2015. So this competence center is dedicated to deep learning, and one of the major questions really to differentiate machine learning from deep learning, which is a subset of machine learning and an umbrella term for multiple types of architectures, all centered around neural networks. So that's a major differentiator, if you like. It built upon neural networks. You have different architectures. Take, for example, convolution neural networks. You have a two-dimensional signal, and you compute and process the signal by a convolution, which is a 2D operation. So for images, for example, you naturally go for convolution neural networks. Assuming you have a temporal signal over time, you take recurrent neural networks, in particular LSTMs, and they can encode those temporal informations. And to make the jump to process video, which is a two-dimensional signal over time, you need a combination of CNN and LSTMs. So comparing this with traditional machine learning methods, we had historically the plateau and a very great time around support vector machines, for example, in combination with particular handcrafted features for the image classification community. So there were two communities, one community designing features, assuming perceptual principles and connecting those features, which are descriptors of images, with methods of classification in a supervised learning setup. So here, for example, we had a great time with back of visual words and support vector machines, but there was a plateau. And suddenly in 2012, where AlexNet came out, we had this great architecture that was 8 layers deep, and therefore deep learning, where we were able to learn end-to-end the feature representation in the convolutional layers with the classification in the fully connected layers. So here finally you have an end-to-end system that is able to learn the features instead of comparing the features and designing the features like histograms of colors or gradients or other things.
I strongly agree on that point. I think the main difference between classical machine learning and deep learning is that actually that feature learning part. So all machine learning algorithms live in a vector space. So it's basically a numerical, mathematically spoken, a numerical method that tries to approximate a function by examples. And this lives in a vector space. And for most problems, actually the hard part is how to get from your image, from your sound sample, from your business data, from whatever you have, into this vector space that you actually can learn a function. And this has been traditionally done by hand. So you had like 1 PhD per problem. That was the scale. Exactly. And with deep learning now, this is basically automatic. Now a deep learning algorithm actually learns the correct representation needed for the actual learning algorithm in one end-to-end, and end-to-end is, I think, a very important part of it, approach. The part about the neural networks, I'm not so sure. Many people say, well, deep learning is about neural networks. I tend to the point of view that actually neural networks are the only known implementation to do deep learning as of now. Okay. But maybe some other method could come around that would have the same properties of deep learning, so feature learning and end-to-end optimization, without neural networks. And actually it's the trend we see in the community that the classical neuron is getting less and less important. We have many more compute units in these large networks, and sometimes we have architectures that actually do not contain a single neuron in the classical sense. So there might be a development that we have to get away from this equality of
the community is based around neural networks?
Historically, yes.
So that's historically from the legacy, and it's interesting because, as you correctly pointed out, more and more specialized types of layers has been created successfully to, first of all, make those networks much, much deeper. A very important breakthrough was residual layers that improved to move backpropagation much further than 10 or 20 layers. This is important because of the so-called vanishing gradient problem. And the other thing is, as you also said, the representation in which your feature space is lying. This is something we don't know a priori, and this is given by the data. So the deep learning network learns that according to the data that we have. And here we're very much driven by the number of samples, and this is also a big difference. Taking, for example, support vector machines, they have a limited capacity. If you add millions of samples, you probably you're not changing the hyperplane, because the supporting vectors defining the hyperplane are the ones that are close to the hyperplane. So it doesn't matter if you add more and more positive or negative samples. However, with a deep learning neural network, like a convolution neural network, you can add layers, you can increase the learn capacity of those layers with the cost of free parameters. And machine learning people don't like free parameters because we have to fit that. That's called training in a supervised learning setup. Therefore, we need more samples. So here, the stream of having more and more data with digitalization, IoT, big data, with the increase of capacity by those networks, together with high performance computation or GPU computing, is giving us actually this sweet spot where we currently are. And this is different than traditional machine learning methods like support vector machines or probabilistic methods. And that's a big, big differentiation between those traditional things and what we currently experience.
Very good, very good. Well, let's talk about the role of Exascale now with deep learning. I want to get eventually to applications, but let's save that for a second. But, so what is the relationship between deep learning and Exascale? As we're heading into the age of Exascale, probably 2020, 2021. So,
Well, at least there's a strong relationship between deep learning and HPC, which we are exploring at this conference. You know, machine learning is traditionally what I would like kind of call single-threaded. Most machine learning algorithms are non-parallel, used to work on a desktop machine. And just with the emerging of deep learning, the machine learning community actually got aware and changed the focus on the importance of parallel algorithms. And we have GPUs play a major role in the computation. And the computational demands of deep neural networks is huge. Yeah. So even mid-sized networks will need in the magnitude of 3 or 4 exa floating point operations during the training. And we are now in a time where actually larger networks and more data leads to better results. So people are driving towards larger and larger and larger problems that need more and more and more compute power. And
suddenly we can also address problems that were out of reach previously. For example, take NVIDIA with the Moonshot project and the Saturn V cluster that they have. Suddenly we're at the edge where we can process this large amount of data automatically and therefore discover things that were previously unseen. And this is what makes so interesting to move the high-performance community, high-performance computing community with deep learning.
And also, for the HPC community, that means that there's a huge group of new users around. Traditionally, you had on your supercomputing centers, you had simulation of all types, climate, materials, whatever, PDE methods, and so on. And now all of a sudden you have a totally new community that thinks differently and has totally different demands, because machine learning demands high throughput of data.
And that breaks the systems, actually.
And it actually breaks the system, so we have a huge impact on the design of new HPC machines, because now data movement really becomes essential in this part.
With respect to that, also, one big difference comparing machine learning to the high-performance computing community is that instead of having large files, single large files or few large files, we have millions of little files. We have released together with Yahoo and the Lawrence Information Laboratory and Flickr data set around 100 million images, the YFCC 100M, and this data set is currently the largest publicly available data set, all Creative Commons, all for research available, but try to get this on disk from one space to another. That's really disk I/O that you have to move around, and this is something you have to organize the data in a way that your GPU, for example, can scan through it and not waste time in looking on disk where those pieces are lying around. It's a huge challenge where your work is working towards it.
So I'm working on the scalability side from an HPC perspective, and it's actually a problem both sides can benefit. It's not like that the machine learning people coming as a customer, it's also the other way around. We have seen in this conference pretty good publications on how deep learning is used to optimize the workflow of HPC systems, how to place the jobs and schedule the data, and so on and so on. And on the other side, also the machine learning community can really learn from the rich experience the HPC community has to offer in decades of research in parallelization and optimization algorithms, all things we actually need. And coming back to your question towards Exascale, you don't need an Exascale machine to do machine learning. You can start that with a single desktop and a fairly sized GPU. But of course, the Exascale program helps the community a lot because there's a lot of investment in new hardware. There will be a lot of development in new systems able to scale to Exascale size. And this is a strong movement and a vibrant community that actually helps. And deep learning community is just like piggybacking on this, influencing the direction it's going, especially in the high throughput demands we will have. And I'm really confident that the new machines we will see towards Exascale will have properties that are well suited for deep learning, and we will.
We currently see it also in the recent developments of GPUs that there is a differentiation that you have inside of those hardware from general purpose to machines that are dedicated for training of neural networks towards inference and application of those networks. There are two different types of requirements. For training, you need to have access to all the data that you have to train your model, and for inference, you apply the model, which is highly scalable, and you have the requirements to apply it in a way where you have low energy consumption of those machines. So you have two different orthogonal types of demands for those machines, and we already see that, so I'm very much looking forward to Exascale, because it means for me deeper networks, better performance, and we still see no saturation in this area, so there is still air where we can improve, and machines help. The other problem in deep learning that is very interesting, neural networks, as compared to traditional machine learning methods, are in their optimization problem not convex. That means that it's more or less a try and error. You cannot guarantee that once you train your neural network, you will land in a global optimal configuration of your network. You can get stuck in a local optima that is telling you that you're good, but you never know if there's a better spot in your network configuration. So it's very important to shorten the cycles between you having an idea and the realization and experimentation, and therefore larger machines, more powerful machines, are helping to speed up the process of developing new innovative layers and types of architectures. Very important, because of this very natural mathematical problem that those networks are not convex in their optimization problem.
Well, this is fascinating. I'm interested, and you mentioned piggybacking and some application. That's what I want to talk about next. This is not just a technical exercise for computer scientists, but this has real-world applications. I'm assuming. Maybe you could tell me which domains might benefit from deep learning and in what way exactly.
Well, I think you could see it on a time scale. There are systems based on deep learning out there, and you might not even know it. There has been all the talk about chatbots, for example, within the U.S. elections, for example. Now there's a professional version of it in first level support, customer support.
So far, no deep learning here.
No?
To my knowledge, no. Everything that I saw.
The chatbots. For example, you see what Baidu is doing. They have this medical assistance system, for example, which is based on deep learning as a chatbot. And you will see also this impact on the job market. It will be that many of the jobs that are fairly standardized office jobs, going through documents, filling out forms, and all of these things, I think these are the first things we will see in widespread applications just around the corner.
So what you can see is in general that the perception, seeing, hearing, speech recognition, translating, those are the things that deep learning really conquered, and surprisingly quickly conquered, because those were the easy things for humans, but very difficult for machines. To understand what's inside of an image was a challenge for a machine. And suddenly we're able to do this. Because of now the machines being able to perceive their environment, we can set up more complex tasks like inference, planning, and suddenly realize applications like self-driving cars, where safety reasons are very important. And here we have the opportunity to change a whole industry that is probably 100 years old, with a product that is now turning to become digital and changing radically how the moving or mobility is being perceived by us all who are using cars. So this is one application, the one with one of the highest impacts on our daily life. Another one, so there are multiple great applications commercially. For me, very important is also to look into areas where we can use AI for good. So where we can use applications to help improve life quality, protect our planet, or save lives. So we're working very strongly towards this with the usage of satellite image data. That's an interesting situation because we're currently at the edge of having scalable access to satellite data for free and commercial use through programs like NASA Landsat or ESA Copernicus with the satellites that they will, or that are already there, and they will launch. So here we have access to this data, a real big data problem with large-scale processing, and this is not only covering the entire Earth, but getting an update, for example, for ESA Copernicus every 5 days for the Sentinel-2 satellite. So here we have temporal changes that we might be able to detect and use, for example, for natural disaster recovery or situation awareness. We were monitoring last year, we started the program with wildfire monitoring in California, a serious, in Portugal, a serious problem. So here, the interesting scientific point of view is those satellites have multiple bands. So combining those bands in a particular way reveals information that standard RGB bands are not giving. For example, vegetation and fire scars, in combining those thermal bands in a particular way. Suddenly you can give the emergency response teams and information. These are the areas that already burned, low probability that new burns will come, and those are the areas where the fire might move, for example, because of vegetation. And therefore you can give this information to the emergency response team to dispatch the resources. Another area where is also very interesting is land use classification. On the entire global scale, we developed a new data set and benchmarked with several deep learning methods with a high probability of up to 90%, 10 different land use classes where you can use those networks to detect where, for example, forests are deforested or fracking sites have been developed where you don't see it from the street, for example, or you can check, for example, where people are doing illegal mining or mountaintop mining. Very important environmental issues that can be now automatically monitored by tools like that. And this goes hand in hand with the so-called United Nations Sustainable Development Goals that have been signed 2 years ago that will monitor progress of humanity till 2030. Great opportunity for research to provide a little bit back to community.
Coming back to the applications, I think you can split it in two categories. One where data actually is available for the community, where we see great progress. So we see great progress in speech recognition, basically is solved in most situations. Translation, if you use Google Translate, that's deep learning.
That's true,
if you use the speech recognition in your car or your personal assistant, that's deep learning. And then we have other areas where the data is owned by companies and it's pretty close. And there we are not seeing that progress. And
we don't know if there is progress.
Yeah, well, but still, the community plays a great role, and the key players, all the big Silicon Valley companies, they have this open data approach. They have everything open, and this is really what drives the development here. And I think there are some branches in the industry that really need to learn this lesson in the long run. If we want to see progress here, if you take the autonomous car, for example, you have car manufacturers getting together, spending millions of dollars in good quality training data and making them public, just to drive the development.
But this is also, I mean, that's also for commercial use. It's outsourcing research to public funded institutes, right? That's also very clever. I mean, technology company from Silicon Valley spending money on annotating a data set for supervised learning, which is very expensive, giving it to the community, looking how everybody is performing, and then buying the team that is best, because they have internal benchmarks, right? So it's something that people from Silicon Valley understood very early, and people in Germany and companies in Germany have to understand slowly. So this is an important difference, but we see that change slowly.
That change is coming. And we're at a high inflection point right now for deep learning is a hot topic on Deep Learning Day here at the ISC conference in Frankfurt.
Yeah.
I think I'd like to bring it back and talk about this community we're in the midst of right now. And I'm sure that's been a big help to you in your own learning, your own research. I wonder if you could say a word about the ISC High Performance Group and what they've meant to your research.
It's one of the two primary conferences in the HPC world, and I think the ISC has understood at a very early stage that machine learning and then deep learning in particular will be a very important class of applications for HPC. And we had the keynote last year was on deep learning this year, and we had one dedicated session last year. This year we have an entire day on deep learning. It's hard to get beyond that, but
that's exactly the point. So for us, deep learning researchers, it's very interesting to meet this community. It's a diverse community, it's a different community, and we can only learn. But this is also that we see with deep learning in general, it's moving from one industry to another and disrupting it, changing the status quo. And this is also happening with high performance computing. And in particular here at the ISC, we see also a lot of potential of deep learning being used inside of the community to improve resource management, etc. So that's really great. So speaking to each other from diverse, so building a bridge between these community islands, that's a huge potential that we have to actually utilize.
And the learning curve is really steep compared to last year. Last year I had a talk at this conference, and most of the conversations I had were on, okay, deep learning, I heard about it, it's a huge hype, what is it exactly? And this year everybody is in the loop, they're asking about details. How do you implement this? How do we scale this? How do we use it for our problems? So I think next year we probably will be talking about deep learning applications in HPC and real HPC solutions for deep learning.
Exactly.
And I expect that deep learning or machine learning in general will be just one of the main topics in HPC for the next decade, alongside the other topics which are still valid, simulation and classic and Exascale. But I think ISC has made the move at the right time. They've seen this coming.
That's true.
And
actually, the discussions having a deep learning day were done far in advance. We started last year after the deep learning track that we had with 3 talks, I guess, at that time, and the keynote from Andrew. This year, the keynote from Thomas Boyle from NVIDIA, also going in the right direction, explaining really the details about deep learning. And from the first discussions to having a whole day dedicated to this topic is a huge move from the ISC and the organizing team to kind of embracing this opportunity and not having a counter reaction as it might be, because that's also something that some industries are having. First of all, some industries are not recognizing the great potential of that and saying that's a hype that will sometimes will be over, and others are just having this kind of counter reaction where they are feeling threatened. And the ISC had really the opportunity, embraced this opportunity and gave a platform to deep learning where now people will meet, network, start collaborations, and next year hopefully we'll see then the results of this fruitful discussion.
Well, I hope so, and I imagine we will. Let's leave it there, gentlemen. Damian Borth, Janis Keuper, I appreciate you talking to me. We will definitely track deep learning on Science Node. We're going to sign off there. I appreciate everybody watching us on Facebook Live here. We've had a great time here in Frankfurt, and this will be our last Facebook Live. Damian, Janis, thank you very much again. Dr. Shane.
See you next year.
Next year, yes, yeah.
Thank you.
Yep. Auf Wiedersehen.
Goodbye.